Okay, what about something like this? So there's some bunch of questions on there on the second assignment, I think second assignment, where it asks you to come up with some factors by which some quantities are changing, right? So you have steel ball attached to a string, it's swung in a horizontal circle at a constant rate. The period is then tripled, so it's increased by a factor of 3. But the radius and mass remain unchanged. And they want to know then, what's the effect going to be on the velocity of the ball? It's going to be changed by a factor of what? The acceleration is going to be changed by a factor of what? And the force is going to be changed by a factor of what? Okay? So to answer these, what we need to do, Seth, why don't you close that up? I need your.
It's the same question.
I need your help on some stuff though. So if we go, oh, there we go. Okay, so I need your help on this though. So I want to know, we got to come up with some kinematic relationships. Let's just summarize all of the relationships we know between various kinematic variables. So what do we know? What are some things we know? And let's just think about what are the kinematic variables that we might want to be able to relate. So centripetal force, right? What else?
Radius.
Radius. What else?
Angular velocity.
Angular velocity. What else? Anything else?
Acceleration.
Okay, centripetal acceleration. Angle. We could, but for uniform circular motion, we don't. We could if we wanted to, but it's not very often. Usually, we're talking about the dynamic variables. Okay. So probably along with angular velocity would be what?
Velocity.
Velocity. Okay. So tangential velocity. And then maybe the only other one I'll add is that. What's that?
Tension.
No. Okay, it is tension lots of times. In this one, it's not. We get the context a little different. It's period. Yeah, it's period. What does period mean?
How often a thing passes a point?
Okay, so it's going to be how often the cycle is repeated, how long it takes. How often would be frequency. How long it takes for one cycle would be period.
So it's revolution.
So the time for one revolution is what period is in this case, right? Because the ball is swinging around on a circle. So the time to make one circle is period, okay? You can remember T as a time because it starts with a T, right? The symbol is a T. Okay, so we want to be able to compare some of those things. What's the simple relationship between centripetal force and centripetal acceleration? Yeah, that's an easy one, right? So that one, no problem. There it is. Okay. What's another one? So that related centripetal force and centripetal acceleration. What about centripetal acceleration? What are the...
Acceleration is delta change in velocity over time.
Change in velocity over change in time. Can we relate centripetal acceleration to some of these other quantities? Do you remember from yesterday? What is it? V squared over R. There you go. Okay, so got another one. Okay, boom, got another one. What else? What's another way of saying, what's the relationship between tangential velocity and angular velocity? Remember, what do we say about that? How is V related to omega?
Wasn't it just equal?
What's that?
Isn't it just equal?
No.
V equals
R omega. There you go. Okay. So if V equals R omega, then what's centripetal acceleration in terms of omega and R? Omega, R omega or squared. Yeah, there you go. R omega squared. Good. If we just make that substitution, right? Okay. Good. We got a lot. These are all things that we know, right? What about, now let's take a look at period. How is period going to be related to, let's say, velocity? Or speed, we might as well say, right? Because the vector is always changing. But the tangential speed, v, how's that going to be related to velocity? I mean, to period. What's the definition of speed?
Just changing distance over time.
Yeah, just distance over time, right? So can you come up with a convenient distance and a convenient time that we could use to calculate how fast the object is moving around the circle?
10. Changing.
Well, maybe.
Radius over t.
Okay, so it's something like that. Now imagine if the steel ball is moving around, you guys are seen from above, the steel ball is moving around in a circle, right? What's a convenient time for us to use to calculate the speed? Maybe, but in
One
general,
revolution.
what is it? 1 revolution. So what's the time for 1 revolution? Maybe. In general, what is it? Yeah, but which one of those quantities represents it? Oh, we're getting there, but which one of these angular, which one of these did you tell me corresponds to the time for 1 revolution? T. So that's the time to make 1 revolution. What's the distance for 1 revolution?
2 pi r.
2 pi r, circumference, right? So there's one we know. Okay, so we know that that tangential speed is equal to 2 pi r over t, right? Circumference of the circle divided by period. Okay? So then, now last one, let's do. Let's relate omega, angular velocity, to t. And you can do this a couple ways. You could just use, you could just make a substitution, right?
2 pi over t.
2 pi over t. Because if I substitute for v, if I substitute r omega, I could divide each side by r, couldn't I? Right? So there's a bunch of stuff, right, that we have. This one makes sense too, doesn't it? Because think about this, let's look at this from a slightly different perspective. In Anglovania, nobody cares how far, what your radius is. It's irrelevant. All they care about is how fast are you rotating, right? So would you agree that in linear land, when we think about tangential velocity, we want to know what's the distance it took to go around the circle, 1 complete revolution, right, divided by time? Well, in Anglovania, it doesn't matter if you're 5 meters away from the center or 10 meters away from the center. It's your angular speed is going to be the same. It's just omega, isn't it? Right? So angular speed omega must just be 2 pi divided by t. Right? What angle did we go through? 2 pi radians in 10 or t seconds. Right? Okay, make sense? Right? So we get all those relationships. Now let's go back and look at this other example. Okay, so, and here they're all summarized for you.
Yay. Yay.
Yay. 5, 6, 7, 10. 9, what do you know? 10. Okay, so what about this guy then? So what do we know here? Let's highlight what we know. So the period is tripled. Okay, so that's something that's changing, right? Period is being multiplied by 3. The radius and mass remain unchanged. Okay, so radius and mass are remaining unchanged. We want to relate the velocity to the period. So which one of these equations, we want to pick an equation that's going to relate T and V with only quantities that aren't changing.
B equals 2 pi
B
r.
equals 2 pi r.
There you go. V equals 2 pi r over T, right? Because the radius is staying the same. So if we take that, let's take that equation, right? So we get V equals 2 pi r over T. What are the things that are changing in this case?
T.
T and
T.
T and V, right? Everything else is staying the same, right? Those are the only quantities that are varying. The other ones are staying the same, right? So if we're going to keep both sides of the equation the same, right? Because it's an equation. If I'm going to multiply the period by 3, what do I have to do to the velocity? Divide it by 3, don't I? Because I multiplied by 3 on the bottom, didn't I? Right?
Yeah.
So that means I've got to do the same thing over there, right? So I'm multiplying the velocity by 1/3. That make sense? To multiply the period by 3. Because they're inversely related, aren't they? Right? Another way to look at that would be, and you take your pick, the other way to look at that would be, what if I multiplied them so they're on the same side? So I had VT equals all that stuff, which is just some constant. Doesn't matter. It's not going to change, right? If I'm multiplying T by 3, what do I have to multiply V by so that they stay the same? 1/3, right? Make sense? Okay, so that answer is 1/3. Okay, what about acceleration? So what's going to be the relationship now? We actually know an extra thing now, don't we? We know velocity is changing by 1/3, period is changing by a factor of 3, radius and mass remain unchanged. So if we want to easily answer this question, ideally we'd like to find an equation that relates acceleration and period only. That one doesn't show up though, does it? But we do have one that relates velocity and period, and we know velocity is changing by 1/3, right? Make sense?
Yeah.
Okay, so for part 2 then, what's that equation going to be? So velocity and period, that's going to be V equals 2 pi r over T, right? Make sense?
Yeah.
Because we know how period is changed. Oops, hang on. We want acceleration, sorry. Wrong one. What am I doing?
So you need the first one?
So we're going to use A equals V squared over R, how about, right? V squared over R, right? R is remaining constant, isn't it? So if you want to, I mean, that's a constant, so we can forget about that one. These are the things that are changing. If V is increasing or is changing by 1/3, then what's that going to do to the centripetal acceleration? Well, look what happens with that. If I take this equation and I rewrite it, so it's got my equal sign, I've got some constant on the bottom that's not going to contribute to anything. Right? On the top, I'm going to take V and I'm going to multiply it by 1/3. But remember, that whole thing is being squared, right? So if I'm going to keep both sides equal, what do I have to multiply the centripetal acceleration by? I got to multiply by 1/3 squared, which is 1/9, right? Okay, see what I'm saying? So that's just 1/9, right? We don't have to use any fancy algebra. We can just look at this in terms of if I'm gonna maintain this proportionality, right? Okay, yeah, fine. What about force? That's an easy one. How is force related to acceleration?
Because I'm a...
So they're exactly proportional, aren't they? So what's the answer for part 3?
1/9.
1/9. Yeah. Right? Okay, make sense?
Can we do some problems?
Yeah. You want to try some of those?
Yes.
Okay. Well, take 10 minutes and do some of those, and I'm going to show you something else.
I lick them closed.
John. Okay, take a look at this real quick. And we're going to go through one of the harder ones too. So what about this? Here's another way to do this that maybe you'll really like. This is kind of a good little trick. So we've got a steel ball, blah, 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 and it's swinging in circular motion, constant speed. The velocity is doubled. The mass and the period remain unchanged. So how is radius related to velocity? What's a way that we can find that only 2 of those are linked? Radius and velocity.
B equals 2 pi r.
2 pi r over t. Okay. What's constant there?
2 pi.
2 pi and t, right?
Yeah.
All that stuff is constant. Only the v and r are varying, right? So try this. Try this one on exercise. How about this? What if you say, let's get rid of all the stuff that's constant, and let's just write this as v is proportional to r, right? If I multiply r by 2, well, v by 2, what has to happen to r?
Multiply by 2.
Has to be multiplied by 2, doesn't it? Right? Make sense? Okay? How about this? Okay, so we know that the answer to this first part, we get 2 and 2, so that's 2. What about the next one? The acceleration of the ball is changed by a factor of what? Well, what's the relationship with acceleration? There isn't one that relates just acceleration to velocity, right? We're going to have to involve, what's our relationship with velocity and acceleration?
V squared over r.
Okay, so acceleration equals v squared over r. Both v and r are changing, right? So we could say then that acceleration is proportional to, in this case we could just leave it an equation because there's nothing else there, but it's proportional to v squared over r. What's r changing by? 2. What's v changing by? 2. So if a is proportional to 2 times v, quantity squared, because the velocity has doubled, over 2r, look what that is. The right side is going to become, if I distribute the 2, I end up getting 4v over 2r. V squared, sorry, right? If I distribute the 2, I get 2 squared times v squared, right? So if a is proportional to 4 over 2 times v squared over r, what's the net result?
2.
2, yeah, it's equal to 2 times v squared over r, right? So in other words, I'm just multiplying this side by 2, so I have to multiply that side by 2, right? See how that works? Okay. All right, what about something like this? Yeah.
In a real world sense,
Mhm.
it says if you double the velocity, then the radius doubles as well.
Mm-hmm.
But what if it's on a string? So it
Okay, you're right. So yeah, let's spend a little time with this. So
tension
let's look at each of these here. If the velocity is doubled, right? So imagine this now. I've got let's say the way you can do this is you can take a straw and you can hang a string through the straw with a weight on it, right? And if I swing the straw around, and I'll demonstrate this for you, but you'll see this in effect. But if you swing the straw around, so there's like a little weight on the end of the string, so it swings in a circle. Does that make sense? So there's going to be a tension that's keeping it moving in a circle. I could swing it at just the right rate so that the tension matches the weight of the object that's being suspended, right? Everybody agree? Okay. So then what happens here to this situation if I'm doing this and the velocity is doubled, but the mass and the period remain the same? So if the velocity is doubling, right,
Yes, sir.
mass and the period remain the same, what has to be happening? The radius has to get bigger, doesn't it? That just makes sense, because if the velocity is doubling, if the period weren't, how could the period stay the same if the radius were the same? If the velocity is doubling, it would be making 2 laps where it used to make 1. But it's only making 1 lap because the period is staying the same. So it must be getting a bigger circumference, right? So the radius is doubling. Make sense? Okay. How about the second part, the acceleration? What's going to happen to the acceleration if the velocity is doubled? Well, what is going to happen there? What would I have to do to this thing if I'm going to double the velocity? I can't hang the same weight there, can I? Right? See what I'm saying? Because it's going to get pulled all the way up and out the tube, right? Would you agree that I would have to increase the force if I'm going to spin this thing faster so there's a greater tension in the string? I'm going to have to increase the force by increasing the weight that's being suspended, right? How much? Well, that much, right? Okay? Okay, so next one. All right, so what about that? So racing on a flat track, a car is going 32.3 meters per second, rounding a curve with this radius of curvature, 56.8. What's the minimum coefficient of static friction that must exist between the tires and the road? So here's what I want you to do. I want you to learn how to use a free body diagram. This is a little tricky, so everybody focus on this, because this is something you'll have trouble with this if you don't see this. All right, so we're used to doing free body diagrams in the past have been, you get a pretty good sense for that, right? How are we going to apply a free body diagram to a uniform circular motion problem? Think about this now. We've got this racing car going around on this flat track, so we're going to have to, here's our perspective. The track is going into the board and around in a circle. So this is going to be the axis of rotation, right? That's going to be the vertical line through the center of the circle, okay? Here's going to be the plane of the track, right there. Okay, so at one moment in time, the car is represented, here's the car, it's getting represented, if I draw a picture, it would just look like this, right? Here's my race car, there's the tires, and it's going into the board, right? And it's going to loop around and come back around like so. Okay. Let's replace the car, as artistic as it is, let's just replace the car with a point. Okay, so if there's my point, what are the forces acting on the car? So there's going to be a normal force, right? The road is pushing up on the car. So we've got our normal force pushing up. What else?
Gravity.
Gravity's pushing down. What else?
Friction.
Okay, there's got to be friction, doesn't there? Now, seen from above, if we took a bird's eye view of this, here's going to be my axis is going to look like this. Whoops, it's going to look like, so here's going to be, this is how we draw a vector coming out of the board. It's got, there's the tip of the arrow, and there's like the bottom of the cone. Say it's a cone-shaped arrow. So that means this thing is coming out of the board, right? Here's this vector, goes right through the middle of that, and here's my car, right? And so the gravity's pointing down, normal force is pointing up, and this car is traveling in a circle, right? Make sense? What's the force that's making this thing go towards the center of the circle, the centripetal force? Friction, right? The proof is, if this is on ice coated with WD-40, this problem would never happen, because the car would just move straight, it couldn't turn. Right? When we introduce friction, all of a sudden it can move in a circle, right? Okay, so that's where we'll finish that up tomorrow.
I figured out what I did. It was grams.
Ah, there you go.
So I knew it was rough, but that was
There you